In this lesson, we're going to discuss expanding logarithms. We'll need three properties to use to expand logarithms. Those three properties are the product property, quotient property, and power property. So we're going to take a look at those three. I'll explain how they work. I'll prove number one at the end, just so you can kind of see how the nuts and bolts of it all works, and hopefully we're good. On the bottom right here, I do have three number rules that we've done before. That is log of any base of 1 is always going to be 0, and that's because when you convert it, b to the 0 power, anything to the 0 power is always 1. The second one is log base b of b, so if those match, then it's just 1. And then the third one, log base b of b to the x power. This one's a little strange, but it is just that x, whatever's in the exponent is your solution. We'll use a couple of those throughout this video. So to move on to kind of an intuition of how these properties are going to work. Once again, logarithms are inverse operations of exponential functions. They basically undo or go backwards. They unpack the idea of an exponent. So we're going to look at the rules of exponents and try to see how they're connected with these logarithms. So I'm going to give you just a couple quick ideas with exponents, and that would look something like this. If I had x to the second power and I multiply it by x to the third power, we're all pretty comfortable with saying, well, we have the same base, we're going to add those exponents. The 2 on this one is saying that there's 2 of those being multiplied together, and that says there's 3 of them multiplied together. So if we're multiplying, that means we can add those exponents together. So this would simplify to x to the 5th power, or 2 plus 3. Actually, let me just write that. 2 plus 3 right there, which is x to the 5th power after you add those together. Now, that property is technically the same as this first property right here. It's just written in a slightly different way because we're using logarithms. If we look at the logarithm has this x times y, and then we're multiplying those two on the inside, and then we end up adding those logs together. Logs are just inverse operations of those exponents, so I hope that makes sense. It seems a little bit weird even on this problem over here that when we multiply, we add, and so we have the same idea on the logarithm. When we multiply, we are going to add those together. You can go a little bit more in general on this if you want to, and that would look like x to the m power multiplied by x to the n power. That would be x to the m and n. Sweet. So that's kind of justifying the first one, which hopefully that one is kind of making sense. The second, the quotient property, is kind of along the same lines. If you're dividing, we got to figure out what do we do with those powers, and that would work or make the same logic for logarithms. So if I had like x to the 10th power and I was dividing that by, x to the 8th power, this would be x to the 10 minus 8. I subtract those exponents. Essentially, I have 10 x's on the top, and I've got 8 on the bottom, and so 8 of them would divide out, so I just get to subtract those exponents. So that's justifying the second logarithm property. If we have a quotient on the inside, we would subtract the two logarithms together. The third one's kind of the hardest one to see. It's pretty straightforward, but it's a little tough to wrap your brain around. But the exponential rule for that one would look something like this. If I had x to the second power, and then I raise that to the third power. So if I raise a power to a power, whenever I do that, I multiply those powers together. So this would give me x to the 6th power. So I end up multiplying these two numbers together. In the log rule, it's kind of working the same way. We've got this log of base b x to the y power, and that log base b of x, that's essentially an exponent, and it's being raised to the y power. The shortcut for this one is just going to be, if you have an exponent on the inside of your logarithm, it just gets to sneak into the front of it like so. And once again, we'll talk more in detail with hard numbers and what that looks like as we start to expand a little bit more. So let's take a look at a couple examples where we're going to use these logarithmic properties to expand a log. Now, the point of expanding a logarithm is to try to break down that inside stuff inside the log and try to make it as simple as possible. So we might have a pretty complicated log to start out with, and we can break it down into a more basic logarithm. We might have more logarithms, but they'll be more basic on the inside. So the first thing I want you to notice here is that we have a quotient on the inside. We've got a numerator and a denominator. So in terms of logs, we're going to subtract those inside of their own logarithms. So I'm going to expand this. I like to just throw a couple little arrows right here. You are going to write log base 7 of 7x minus log base 7 of y. So we had a quotient on the inside. We're going to subtract those logs together. Okay, so that's an expanded version of that log. Now, we did have more logarithms present. However, we have simpler things on the inside of each of those logs, and sometimes that could be beneficial down the road. Okay. One more side note on this expansion is technically this 7 and the x are being multiplied together. And so we can actually use rule number 1, the product property on that. And we can actually expand this one one step further. So we can write this as log base 7 of 7 and then plus log base 7 of x. So we had the product between 7 and x. Those are the factors of it. And we can break that apart, split that up into each of their own logs. Now we still have this subtract log base 7 of y. We got to tack that on the end as well. So we're just going to write this at the end here, log base 7 of y. Okay, so that's looking pretty good. One more small thing, if you notice on my 3 little properties back here, that I have this first rule that says, if I have log base b of b, anytime those numbers match, it's always 1. So if I go back to my last problem right here, this log base 7 of 7, that will just equal 1. So I can actually simplify that down to 1 plus log base 7 of x minus log base 7 of y. And that would be the fully expanded version of that logarithmic expression. We're going to take a look at a couple more examples and see what this is going to look like. The next example I have up here is log base 4 of 5x to the third y squared. I do technically have 3 products in there. I have the 5 multiplied by the x cubed multiplied by the y squared. If you want, you can do this in one step. We have 3 terms that are getting multiplied together. So each of those can get its own logarithm. So that's usually where I would start with these expanding logarithms. See how many terms are on the inside and see if we can break that apart. Okay. One thing to say is the base is base 4 on this one. And so we just leave the base alone. We don't have to change the base. Same as on the exponential rules. We don't want to change those bases. Okay. So I'm going to expand this. I'm going to write this as log. Oops. Didn't mean to do that. Sorry. Log base 4 of 5. Since it's a product, we're going to add those. Log base 4 of x to the third. And then plus log base 4 of y squared. So that's using the product rule, rule number 1 for our logarithms. Okay. Typically, you're going to use rule number 1 or number 2 first in your expansion. And then the last thing we usually do is if we have an exponent, so notice that this 3 right here is an exponent and that 2 is an exponent, both of those can move to the front of their respective logs. So log base 4 of 5, that didn't have any exponents, so we're just going to leave that one alone. And then plus this 3 right here can move to the front to the coefficient. So it becomes 3 log base 4 of x. And then the 2 on the y gets to move to the front. 2 log base 4 of y. So that would be the fully expanded version of that one. These base and numbers don't match here, so there's no simplifying to do on that one. It looks pretty good, and that would be the fully expanded version of that. So this one's a little bit more complicated. We got a little bit more going on here. We have, looks like 4 total terms on the inside. So we should break this apart and do 4 total terms or 4 total logs together. So I kind of see these as like multiplied or product on the top there. And then we do have 1 quotient. So we're going to split this apart. So I would write this first as log base 2 of 8 plus log base 2 of x squared plus log base 2 of y to the fourth. And then that z to the third is on the bottom, so it's a quotient. It's going to get subtracted. So it'd be log base 2 of z to the third power, like so. So we're doing pretty good there. The exponents now, using that third property, we can move to the front. Just simplify the inside, make those variables not quite so complicated. So this 2 I can move in the front on the second one. So this would be plus 2 log base 2 of x plus 4 log base 2 of y, and then minus 3 log base 2 of z. A little extra on this one, we have log base 2 of 8. Remember from previous videos, this 2 right here is counting how many times multiplied it goes into that 8. So 8 is really 2 to the third power. And so if you want to write it that way, you certainly can. But this is really log base 2 of 2 to the third power. Anytime I can get the base to match the base here to match the base there, that's a good thing, because the exponent is just my answer for that one. And so this answer on the left here would just be a 3. So I can replace all of this stuff right here with a 3. So 3 plus those logs. And that'd be the simplified version of that, or the expanded version of that logarithm. So last one of the big expansions, and then I will jump off the deep end a little bit here and attempt to do one nice little proof for you, and then we'll be good. So expand the logarithm, log base 3 of all of that stuff. There's a couple terms on the inside there. Looks like we've got the radical on the top and the 7 on the bottom. So the first thing I see is a quotient, so I'm going to use the quotient rule for this one. So we're going to go log base 3 of the numerator, so that is 3x plus 5. And then the 7 is a quotient. It's going to get subtracted. Log base 3 of 7. Not very good there. Okay, so that looks pretty good. The log base 3 of 7, there's not a whole lot I can do with that. Technically, this square root power right there, that's actually a 1/2 power. That's the same as raised to the 1/2. So let me write that out just so you can see it really good. Log base 3 of this would be 3x plus 5. All to the 1/2 power, and then we're not going to do anything with this caboose here. We're going to leave that alone. All right, so we've got a 1/2 in the exponent, which means this 1/2 can slide in the front as a coefficient. So I can write this as 1/2 log base 3 of 3x plus 5, and then minus log base 3 of 7. All right, and there's your fully expanded logarithm for that one. There is just one more thing to say about this. There's not much I can really do with this crazy inside term right here. We are adding these terms on the inside, and we do not have a good rule for that. There's not a nice way to clean that up. You're kind of stuck there a little bit. And there's an exponential rule that or an idea that mirrors that. That's kind of the same, but if there's addition or subtraction there, you just got to leave it alone. There's not much you can really do with that. All right, sweet. So I just thought I'd prove this, maybe rule number 1. So this is just the way that I think about how this property works. Is I think about it really in terms of exponents. So I want to rewrite these as exponents. So I'm just looking at log base b of x and then log base b of y. So we're going to check those two out if I can. So I just set them equal to arbitrary numbers. Just set them equal to m and set them equal to n. Just kind of picked a couple random numbers there. So what I'm going to do is I'm going to convert both of those back to exponential form. So remember, when we convert, we always start with the base. The base on this is b, and it'll be raised to the m power equals x. That's the corresponding exponential equation for the logarithmic equation. I can do the same thing for the one on the right. This would be b raised to the n power equals y. And that's looking pretty good. So now what I want to do is I want to mash those together. I want to multiply those sides together. So essentially I'm going to take this left thing, this b to the m, I'm actually going to give myself a little bit of space, equals x, and I'm going to multiply both sides of that equation by this true statement. So I'm going to multiply this by b to the n, and then multiply this by y. So I've essentially multiplied both sides of the equation by a same thing, an equal thing. Okay, so we're going to use our exponential rules now on the left here. This would be b raised to the m plus n would equal xy. And now once I've got that together, let's convert that back to a logarithm. So the base is b, and so we're going to write that as log base b. And we're going to swap out the x and y. So log base b of xy equals m plus n. And oh, geez, we're there. We're home free. We got m plus n. We've got this thing right here. Well, I've got m right here and n right here. Let's just go ahead and switch those out. So we're going to go log base b of xy equals m, which is log base b of x, plus n is log base b of y. And so there's your hallelujah. Got it. Proved it. Sweet. Well, hope that worked out for you. And yeah, email us or your teachers if you got any questions. Thanks.